Tonight, we are following a spacecraft that is not yet in space. It is standing inside a strange room on Earth, surrounded by blue foam spikes, metallic walls, and instruments designed to imitate the silence of the void. This is PLATO, Europe's next great planet hunter, and its latest test was not about surviving a rocket launch. It was about learning whether its own electronics can live together without getting in each other's way. The mission's name is PLATO, short for Planetary Transits and Oscillations of Stars. Its target is one of astronomy's most intimate questions: how common are worlds like Earth, and what do their stars reveal about their history? Before PLATO can study distant planets, every signal inside the spacecraft must be trustworthy. A tiny electrical disturbance could become a false planet, a lost measurement, or a mystery that exists only inside the hardware. That is why the newest milestone is so important. In July 2026, the European Space Agency reported that PLATO had completed a series of electromagnetic compatibility tests at ESTEC, the European Space Research and Technology Center in the Netherlands. The spacecraft cleared the final major examination in a long sequence of trials designed to prove that it is ready for launch. The test chamber looks almost unreal. Its walls, ceiling, and floor form a conducting enclosure, a giant Faraday cage that screens out outside electrical interference. Across those surfaces are dense rows of foam cones. They absorb radio frequency energy and sound, reducing reflections and helping engineers create an environment that behaves more like empty space than an ordinary laboratory. Inside, PLATO's electronic systems were switched on and commanded remotely. Engineers watched the spacecraft as its instruments, computers, power systems, and communication hardware operated together. They were looking for unwanted signals, unexpected interactions, or what engineers call crosstalk, one subsystem accidentally disturbing another. Crosstalk is invisible, but its consequences are not. Imagine trying to hear a single whisper while dozens of people are speaking through the same wall. Now replace the voices with high-speed digital clocks, power converters, transmitters, sensors, and long electrical cables. Each system produces energy, and every other system must be protected from it. For a normal machine, a little interference may be annoying. For a space observatory measuring changes in the brightness of stars, it can be catastrophic. PLATO will search for planets by watching stars dim when a world passes in front of them. That dip may be extremely small, and the instrument must know whether it came from a planet, a stellar fluctuation, or a pulse of electrical noise. PLATO is designed around an unusual and powerful idea. Instead of staring at a few stars through one narrow field of view, it will carry a large collection of cameras and observe huge regions of the sky at once. The mission is expected to monitor hundreds of thousands of bright stars, searching for the repeated shadows of planets crossing their faces. The spacecraft is also a kind of stellar seismologist. A star is not a perfectly smooth ball of light. It vibrates, boils, rotates, and changes. Those subtle variations can reveal its age, size, internal structure, and chemical history. By combining the star's own oscillations with the orbit of a planet, PLATO can help astronomers calculate the architecture of an entire planetary system. But precision astronomy begins with engineering discipline. The spacecraft must be quiet in every possible sense, mechanically stable, thermally controlled, optically clean, and electrically well-behaved. A detector cannot simply be sensitive. It must be sensitive only to the phenomenon scientists are trying to measure. The electromagnetic test was one chapter in a much longer exam. Earlier in 2026, PLATO completed vibration and acoustic tests, which simulated the violent shaking and sound pressure of launch. It then spent about a month inside ESA's large space simulator, where engineers exposed it to space-like thermal and vacuum conditions. These tests are not theatrical rehearsals. They are attempts to reveal failure before the rocket leaves Earth. In space, a loose connection cannot be tightened by hand. A hot component cannot be replaced during a routine service call. If two systems interfere with one another after launch, engineers may have only software commands and carefully limited operating modes with which to respond. The Maxwell test chamber addresses a different danger. A spacecraft in orbit is surrounded by radio signals, but it also generates its own electromagnetic environment. Power flows through it, computers switch rapidly, instruments send data, and communication systems transmit information back to Earth. The compatibility campaign asks a simple question with complicated consequences: can all of that happen at once? The answer matters especially for Plato because its science depends on stable, long observations. A planet may take days, weeks, or months to complete an orbit. The mission must recognize a pattern that repeats across time, not just a single moment of darkness. Any persistent electrical problem could imitate a rhythm in the data or hide a real one. The spacecraft's physical appearance hints at that precision. Plato's observation system is built around many telescopes working as a coordinated array. Together, they create a broad view of the sky while preserving the sensitivity required for photometry, the measurement of light. The mission will eventually occupy a special orbit around the Sun-Earth Lagrange point 2, far beyond Earth's night side. At that location, the observatory can maintain a stable relationship with Earth and the Sun while looking outward into deep space. It will not be close to the planets it discovers. Instead, it will watch stars from a calm vantage point, turning minute variations in starlight into information about worlds that may be hundreds or thousands of light-years away. There is something humbling about the chain of events. A spacecraft is assembled by human hands, tested inside a room lined with foam, launched on an Ariane 6 rocket, and then used to investigate planets no human could ever visit. The bridge from a laboratory in Europe to an alien sunrise begins with eliminating interference in a circuit. ESA says Plato has now cleared the last remaining major exam in its launch campaign. The planned launch is March 2027, with Arianespace preparing the mission for an Ariane 6 departure. That date is still a waypoint, not the end of the story. Once launched, Plato must unfold, calibrate its instruments, settle into its observing orbit, and prove that its measurements remain as clean as they were on Earth. Then the waiting begins. The most exciting discoveries may not arrive as dramatic images. They may appear first as a shallow, repeated dip in a graph, a pattern in a star's brightness that survives every test of interpretation. A planet will announce itself not with a flash, but with a shadow. From those shadows, astronomers can estimate a world's size and orbit. From the star's oscillations, they can estimate the system's age and scale. With follow-up observations from other telescopes, they may learn whether a planet is rocky, gaseous, hot, cold, young, or ancient. Plato's purpose is to transform the search for Earth-like worlds from a collection of remarkable examples into a statistical portrait of planetary systems. That portrait could change how we see our own neighborhood. If small planets are common, Earth may be one member of a vast family. If the conditions that produce temperate worlds are rare, our planet may be more unusual than intuition suggests. Either result would deepen the question of how planets assemble, how atmospheres survive, and where life might have an opportunity to begin. The quiet room at ESTEC is therefore connected to some of the loudest questions in science. The foam spikes are not decoration. The sealed walls are not a backdrop. They are part of a careful argument that when Plato finally looks at the stars, the signals in its data will belong to the cosmos, not to the spacecraft itself. For now, Plato remains on Earth, surrounded by engineers and test equipment. But with its electromagnetic compatibility campaign complete, another boundary has been crossed. The Planet Hunter has demonstrated that its many electronic voices can share the same machine without drowning one another out. Soon, that machine will leave the laboratory and turn toward the sky. And when it begins watching stars fade by fractions of a percent, it may reveal a universe filled with worlds that have been crossing in front of their suns for billions of years. The final test on Earth is complete. The search for distant Earths is about to begin.